In this video, we're going to practice maximizing or minimizing a function. So for this example, let's say that a box's length is twice its width. And if we look at the 3 dimensions of the box, we know that they sum to 60 centimeters. The question is, what is the maximum volume of the box? All right, so first thing we might want to do here, maybe come up with a sketch that will help us organize a little bit of our information. So let's say here's the length of the box. The length is twice the width. So let's do something like that. Okay, and then the box has some height as well. Let's draw our height in the vertical direction. Okay, and there is a sketch of our box. So let's see if we can come up with some variables for this problem. Let's let x represent the box's width. Okay, so we can label that on our sketch there. That dimension there is the width. That's x. We know that the box's length is twice its width. So we don't need a separate variable for the length. We know that the length is 2x. Okay, and we don't know the height of the box. So let's let h represent the box's height. And we can label h on our diagram as well. Now we have got one piece of information in the question that was given to us. We know that the 3 dimensions sum to 60 centimeters. So let's write given information. We know that if we take the width, x, plus the length, which is 2x, plus the height, that these 3 quantities sum to 60 centimeters. Okay, so that's our given information. And we should also write down what we're trying to do in this question. So we are trying to maximize the volume of the box. So let's maximize V, the volume, and we get the volume from taking the width times the length times the height. Okay, and that way we have now incorporated all the information given in the question. So generally when we're maximizing or minimizing a function, this is how the question starts out. You've got one piece of given information and you've got a quantity, a function that you are trying to maximize or minimize. Now one thing that makes the problem tricky as it is right now is when we look at our function, it's a function of 2 different variables. We've got x's and h's in here. So what we need to do to get going is replace h. And we're going to be able to replace h using the given information. So this is another common pattern that we run into in maximizing or minimizing a function. You need to replace one of the variables with using the given information. Okay, well we know from the given information that h is equal to 60 minus 3x. That's just from using this equation here and solving for h. So let's actually plug 60 minus 3x in for h and we'll come up with a nicer function for v. So now instead of just calling this v, I'm going to call it v of x because it's now going to be totally in terms of x. Our volume now looks like x times 2x and h, instead of h, I'm going to write 60 minus 3x. All right, so now we can really get into some calculus. Let's do a little bit of simplifying here just to clean up this function a little bit. So our volume function looks like 2x squared times 60 minus 3x. Now let's actually expand that out, just simplify it a little bit more. So it looks like 120 x squared minus 6x cubed. Okay, so we've now got a nice looking function v of x. Okay, well now we're going to go back to some of our techniques that we saw in the curve sketching section. We are now going to find all the relative maximum points for this function. So let's find all the relative maxima. Remember, what we're trying to do is maximize the volume of the box. So that's the same thing as saying find all the relative maxima for the function v. Well, the way we're going to do that is find the derivative. We're going to find v prime, which will be 240x minus 18x squared. And we're now going to look for critical points for this derivative here. Now, thinking back to curve sketching, remember we said critical points are places where the derivative is either equal to 0 or undefined. And when we're dealing with polynomials, remember our function, our derivative here is never going to be undefined. So this case here of having the derivative undefined, it's not needed when v prime is a polynomial. Okay, so that just summarizes again some of our ideas from curve sketching. If we've got a polynomial here, it's just a matter of taking the derivative and setting it equal to 0. Only if our derivative is a rational function do we need to worry about whether it's undefined or not. All right, so we're going to take 240x minus 18x squared, and we are going to set it equal to 0 and try to find our critical points. In setting this function here equal to 0, let's try to factor it. We might notice that each of these coefficients here are divisible by 6, and we can also pull out an x from each of our terms there. So this will factor as 40 minus 3x, and that's all equal to 0. Okay, well, from the first factor, one option is that x is equal to 0. And from the second factor here, the other option is that x is equal to 40 over 3. So often in these maximizing or minimizing problems, we end up with a couple of options for x. So let's see how we can check which x value is the right one. We're going to check this using the second derivative. Now, at this point, it might be obvious to you that x equals 0, that's not a very good choice. Remember, x represents the width of our box, so x equals 0 really doesn't correspond to a physical three-dimensional box. But let's run through the general process anyway, because in some problems, the choice will be a little bit more subtle. So our second derivative, v double prime of x, it might help just to remind ourselves what the first derivative looked like. So just write it down again. V prime of x was 240x minus 18x squared. That's this function that we had written up here. So taking the second derivative then, we're going to get 240 minus 36x. All right, so what we're going to do is plug each of our x values into our second derivative. So we'll plug each of them in here. Just make this a little bit easier to read. Plugging into the second derivative. And all we're looking for is the sign. So just trying to figure out, is it positive or negative? Well, if we plug 0 in here, we get 240. That's a positive number. If we plug 40/3 into our second derivative, you could check with your calculator that it's going to come out negative. Okay, so again, thinking back to our curve sketching techniques, let's see what this tells us. If the second derivative of a function is positive, that tells us that the function is concave up. So it has this kind of a shape. And if a function is concave up and we have a relative max or a relative min, by our picture here, it's got to be a relative minimum. So second derivative being positive means the function is concave up. That means we're looking at a relative minimum from our critical point here. Now, if our second derivative here is less than 0, then it tells us that our function is concave down, and it tells us that our critical point that we found, well, just based on this picture, it must be a relative maximum. And in this problem here, we were trying to find the maximum volume of the box, so 40/3 is the critical point that we're interested in. So we can now say that the maximum volume happens when x is equal to 40/3. Okay, and that's measured in centimeters just based on the units in the original question. Now, it's very important here at the end of the problem to actually answer the question. And the reason I say that is that these questions can be worded in a variety of different ways. So this particular question asks for the maximum volume of the box. That means that just saying x equal 40/3, well, that doesn't answer the question. We actually need to say what that maximum volume is. Okay, so let's go back to previous steps in the question. Let's look for a step when we actually had a formula for V. So looking back, we said that our volume was x times 2x, and after we had replaced h in this formula, we ended up with something like 60 minus 3x. Okay, so this might be a good step to look back to. We now just want to figure out what happens when we plug in 40/3. So volume when x is 40/3 is going to be 40/3 times double that, so times 80/3 times 60 minus 3 times 40/3. All right, so with a little bit of simplifying here, the 3's in that term there are going to cancel, so it's looking like 40/3 times 80/3 times 20. We can do this on the calculator if you like. You get 64,000 divided by 9, and because we're talking about volume, that'd be cubic centimeters. So the maximum volume of the box, biggest possible volume that we could come up with, is 64,000 centimeters cubed. Okay, in other variations of the question, it might say, what is the width of the largest box, or it might ask for some other variation like that. So we should be prepared to give some other answers as well. Remember, x in this problem represented the width. So the width here is 40/3. If we wanted the length of the box, could remember that the length is exactly twice the width, so the length of the box is 80/3 centimeters. The question could easily ask for the height of the box as well. Remember that that height is represented by h. Okay, so that's really our 60 minus 3x is representing our h. And in this step here, we figured out our height was equal to, well, 60 minus 3 times 40/3, we worked that out as 20 centimeters. Okay, so always a good idea just to reread the question and actually give the answer in terms of what specifically was asked for. In this case, we gave the maximum volume.